Before there were ships, before there were sharks as we know them, before a single human eye had ever touched the horizon, the ocean was already hiding monsters, not mythical ones, real ones. Imagine standing at the edge of an ancient shoreline nearly 100 million years ago. The air is warmer, heavier. The world feels unfamiliar, almost unfinished. There are no distant engine sounds, no aircraft trails overhead, only wind and the slow, endless breathing of a prehistoric sea. At first glance, the water looks calm, peaceful, even but the surface is lying. Because beneath it, far below the gentle shimmer of sunlight, something vast is moving through the dark, and it is not alone. Prehistoric oceans were not just different from today's seas, they were overrun by giants. Creatures of impossible scale patrolled these waters with quiet dominance. Marine reptiles longer than modern buses, fish that could swallow a human whole without slowing down. Apex predators built not just to survive, but to rule. This was the true age of oceanic gigantism, and it didn't happen by accident. To understand why these ancient waters produced so many oversized creatures, we have to strip away the familiar comfort of the modern ocean and step into a world operating under very different rules. Because millions of years ago, Earth itself was behaving differently. Sea levels were higher, temperatures were warmer, oxygen moved through the oceans in ways that favored size, sometimes extreme size. In evolutionary terms, the prehistoric ocean wasn't just habitable, it was generous. Gigantism, in biology, rarely appears without reason. Growing large demands enormous energy, more food, more oxygen, more stability in the environment. In most ecosystems, those requirements create strict limits. But the ancient seas were unusual. They offered abundance. Warm global climates during periods like the Mesozoic era meant polar ice was minimal. With less ice locking away water, the oceans expanded, flooding vast continental shelves. These shallow coastal seas became biological superhighways, rich in nutrients, flooded with sunlight, and teeming with life at the base of the food chain. Where plankton blooms, life multiplies. Where life multiplies, predators evolve. And where predators compete over millions of years, size becomes a weapon. But the story isn't just about food. It's about physics. Water supports weight far more effectively than air. On land, gravity punishes animals that grow too large. Bones must thicken, joint strain, movement becomes costly. But in the ocean, buoyancy changes the rules entirely. Massive bodies can glide with surprising efficiency. Length becomes an advantage. Bulk becomes momentum. In prehistoric seas, evolution discovered something important. Being bigger often meant being better. Better at migration, better at heat retention, better at surviving attacks, and sometimes far better at hunting. Yet, here's where the mystery deepens, because not every period in Earth's history produced giants like this. Even today, in oceans filled with whales, the sheer variety of massive predators we see in the fossil record is unusual. Something about those ancient oceans created the perfect storm, a convergence of temperature, oxygen levels, ecological opportunity, and evolutionary pressure that repeatedly pushed marine animals toward extreme size. But abundance always carries a shadow, because when ecosystems become rich, competition becomes brutal. And in the prehistoric ocean, the race to grow larger wasn't peaceful. It was an arms race unfolding over tens of millions of years. Predator versus predator, hunter versus hunter. Each generation nudging the limits of biology just a little further. Some species grew longer, some grew heavier. Some evolved jaws that turned the ocean itself into a hunting ground of constant danger. If you had slipped beneath the surface back then, even for a moment, the experience would feel profoundly different from modern seas. Today's oceans, vast as they are, often feel empty. Ancient oceans did not. They were crowded, alive in every layer. From the sunlit shallows to the cold, crushing depths, movement was constant, life was abundant, and somewhere in that layered blue world, giants were always nearby, even when you couldn't see them, especially when you couldn't see them, because the most successful prehistoric predators didn't need to announce their presence. They simply appeared. And that raises the question that pulls us deeper into this mystery. What exactly made those ancient oceans so perfectly designed for giants? And why did that era eventually come to an end? In the next section, we descend into the environmental secrets that turned prehistoric seas into the ultimate breeding ground for ocean titans. If you could sample a drop of prehistoric seawater, you would notice the difference almost immediately. Not in color, not in taste, but in what it could support, because the ancient oceans were not just bigger in size, they were richer in energy. And in nature, energy is everything. The modern ocean, for all its vastness, is surprisingly sparse. Much of it is what scientists call a 40 marine desert teddy, enormous stretches of water with relatively little life. Nutrients are often locked away in the deep, food chains are efficient, but thin. Even today's giants, like the blue whale, survive only by exploiting very specific seasonal booms. But during large stretches of the Mesozoic world, the rules were different. Warmer global temperatures kept the planet's climate unusually stable. With little polar ice to disrupt circulation, the oceans mixed in ways that constantly recycled nutrients upward. Coastal flooding created immense shallow seas, warm, sunlit, and biologically explosive. Imagine entire continental regions submerged beneath relatively shallow water, glowing with plankton blooms visible even from space, if anyone had been there to see them. These weren't just productive waters. They were Cindy overflowing Indetine. At the base of the food web, microscopic phytoplankton multiplied in staggering numbers. These tiny organisms, powered by sunlight and dissolved nutrients, formed the living foundation of prehistoric marine ecosystems. And when the bottom of the pyramid expands, everything above it begins to grow. Zooplankton population surged, small fish followed, then mid-level predators, each layer feeding the next, energy stacking upward like a biological pyramid built to support something massive at the top. This is one of evolution's quiet laws. If an ecosystem can afford giants, eventually giants will appear. But food alone doesn't explain the full story, because growing enormous is physiologically expensive. It demands oxygen, lots of it, delivered efficiently through blood, muscle, and tissue. Without sufficient oxygen availability, large bodies become liabilities rather than advantages. And here, again, the prehistoric ocean offered unusual help. Evidence from ancient sediments suggests that many Mesozoic oceans were well oxygenated in key surface and midwater regions. Warm temperatures increased metabolic activity, while strong circulation patterns prevented widespread stagnation in many marine basins. For large marine animals, this created a rare biological sweet spot: plentiful food, stable temperatures, reliable oxygen. A combination that doesn't appear often in Earth history. But perhaps the most overlooked factor was something more subtle: fun time. Evolution doesn't produce giants overnight. Size increases slowly, generation by generation, through a process biologists sometimes call Fidey-Cope's rule. The tendency for lineages to evolve toward larger body sizes when ecological conditions allow it. And during long stretches of the prehistoric era, marine ecosystems experienced something unusual: relative stability over millions of years. Fewer abrupt climate collapses, long-lived food webs, expansive, connected seas. In that kind of environment, evolutionary experiments had room to run. Predators that were slightly larger often had advantages. They could travel farther, dominate prey, and survive longer periods without food. Over time, natural selection quietly favored bulk, not always, not everywhere, but often enough to reshape the oceans. Still, abundance creates opportunity not just for growth, but for rivalry. Because as more giant predators emerged, they began to overlap, to compete, to encounter one another in the same hunting grounds. And in the prehistoric ocean, competition did not stay gentle for long. Fossil evidence reveals something striking. Many of these marine giants weren't simply large. They were seen heavily armed, handing massive bite forces, reinforced skulls, serrated teeth built not just for fish, but for bone. This was not a peaceful world of oversized filter feeders. It was an ecosystem sharpening itself, an evolutionary arms race unfolding beneath the waves, and the bigger the animals became, the higher the stakes grew. Because in a world full of giants, being large didn't just make you powerful, it made you a target. In the next section, we meet the apex predators that turned prehistoric oceans into one of the most dangerous environments Earth has ever known. When giants became hunters, size alone does not create a monster. Plenty of animals grow large and live quietly, grazing, filtering, drifting through the world with gentle indifference. But in the prehistoric ocean, something different happened, because many of its giants did not evolve to be peaceful. They evolved to hunt. If you could descend slowly into a mid-Cretaceous sea, the first thing you might notice is the abundance of life. Schools of fish moving like liquid metal, soft-bodied creatures drifting in layered clouds, reptiles surfacing briefly for air before slipping back into the blue. It would feel alive. Vibrant, almost safe, and then the pattern would break. Somewhere in the distance, the water shifts, not violently, not dramatically, just enough to unsettle the rhythm of the scene. This is how apex predators often announce themselves: by disturbing the calm. Among the most formidable rulers of these ancient seas were the Moctomosasaurs, said marine reptiles that looked at first glance like oversized lizards. But that first glance would be dangerously misleading. Fully grown, some species stretched over **15 meters long. Their bodies were built for speed, long, muscular tails driving them forward with terrifying efficiency. Their jaws were double-hinged, allowing them to open wider than most modern predators could manage. And inside those jaws, rows of backward-curving teeth designed not just to bite, but to hold. Fossil evidence tells a chilling story. Mosasaurs didn't specialize in one type of prey. They were opportunists in the purest sense: fish, turtles, seabirds, even other marine reptiles, sometimes even each other. This is the hallmark of an ecosystem under pressure. When food is abundant, but competition is fierce, predators diversify their targets, flexibility becomes survival. And over millions of years, natural selection begins to reward the most versatile, and often the most aggressive hunters. But mosasaurs were not alone in this race toward dominance. Sharing the seas were the zoosaurs, some with long snake-like necks that allowed them to strike into schools of prey with surprising precision. Others evolved massive skulls and crushing bite forces that suggest a very different hunting strategy, one built for overpowering large, struggling animals. Multiple predator lineages, different body plans, one shared trajectory: further bigger, faster, deadlier, ***, and then there were the fish. Because while reptiles often dominate our imagination of prehistoric seas, some of the most powerful hunters were not reptiles at all, but enormous predatory fish evolving along their own path toward gigantism. In these crowded waters, hunting was not simply about speed, it was about energy economics. A larger predator could travel farther between meals. It could consume bigger prey. It could survive longer periods of scarcity. Over evolutionary time, these advantages compound, slowly nudging average body size upward generation after generation. But with increased size came increased visibility. A 2-meter predator can disappear into complexity. A 15-meter predator changes the water around it. And this is where the prehistoric ocean became truly dangerous. Because as multiple giant predators evolved simultaneously, their hunting territories began to overlap. Bite marks found on fossilized bones reveal encounters that were anything but peaceful. Some marine reptiles show clear evidence of surviving violent attacks, injuries that later healed, suggesting lives spent in constant risk. The ocean had become a competitive battlefield, not a single dominant hunter, but many, each species pushing the limits of biology in its own direction, each encounter carrying real stakes. And in this kind of evolutionary arms race, there is a powerful feedback loop at work. When predators grow larger, pre-species respond. They evolve speed, armor, schooling behavior, camouflage, which in turn pressures predators to become even more efficient, even more powerful, even more massive. Over millions of years, this feedback loop can reshape entire ecosystems, driving the emergence of animals that seem almost unreal to modern eyes. But here is the deeper truth hiding beneath the fossil record. Gigantism is not just about opportunity. It is about sooty pressure, and in the prehistoric ocean, the pressure was building because ecosystems that produce many giants rarely remain stable forever. Eventually, something shifts. In the next section, we uncover the hidden biological advantages that made extreme size such a powerful survival strategy, and why evolution kept pushing ocean predators to grow even larger. ***. There is a quiet moment in the open ocean, when everything seems suspended, no waves breaking, no obvious movement, just endless blue fading into deeper blue. It feels empty. But to the creatures that evolved here millions of years ago, this vastness presented a very specific challenge. How do you survive in a world where food can be far apart, and danger can come from anywhere? ***. For many prehistoric marine animals, evolution answered with a simple but powerful solution: grow bigger. Not just slightly bigger. Massively bigger. Because in the ocean, size is not merely about dominance, it is about efficiency. One of the most important advantages of large body size in water is something physicists call phase scaling efficiency. As animals grow larger, their volume, and therefore their energy reserves, increases faster than their surface area. In practical terms, this means large marine animals often use severity per unit of body mass to move through water than smaller ones. In the prehistoric seas that mattered enormously, food wasn't evenly distributed. Prey moved in shifting schools. Nutrient blooms came and went. For predators traveling long distances between successful hunts, efficiency meant survival. A larger hunter could cruise longer, wait longer, endure longer periods without eating. And over millions of years, natural selection quietly favored the animals that could stretch those limits. But energy efficiency was only part of the story. The ocean is cold, often brutally cold below the surface, and temperature control is one of the greatest challenges any marine animal faces. Smaller bodies lose heat quickly, larger bodies retain it. This is known as tendigantothermy in prehistoric seas, where temperature layers could shift dramatically with depth. Large body size provided a thermal buffer. Massive predators could dive deeper, stay submerged longer, and exploit hunting zones that smaller competitors simply couldn't tolerate. Size expanded territory, and territory meant access to more food. But perhaps the most immediate advantage of being enormous was something more direct: fighting protection. Asterisk, in an ocean increasingly filled with large predators, being small carried constant risk. Juvenile mortality in marine ecosystems is notoriously high even today. In the prehistoric world, crowded with aggressive hunters, that danger was amplified. Growing larger reduced the number of animals that could realistically threaten you. At a certain size threshold, many predators simply stopped being prey, and evolution noticed. Fossil growth patterns suggest that many marine reptiles and large fish species experienced rapid growth early in life, almost as if their biology was racing toward that safety threshold as quickly as possible. Grow fast, grow large, survive. Yet here is where the story becomes more complex, because gigantism is never free. Massive bodies require massive food intake. They demand stable ecosystems capable of supporting high-energy predators, and they create a dangerous evolutionary trap. Once a lineage becomes specialized for extreme size, it becomes harder to adapt if environmental conditions begin to shift. In other words, what makes giants powerful can also make them fragile, and by the late stages of the prehistoric era, subtle warning signs were already beginning to appear in the oceans. Climate patterns were fluctuating, sea levels were shifting, food webs, once reliably abundant, were starting to show stress in certain regions. At first, the giants kept growing, kept hunting, kept ruling the seas, but ecosystems have limits. And when those limits are crossed, even the largest predators on Earth can find themselves vulnerable, because the same forces that once built an ocean of giants were slowly beginning to change. In the next section, we uncover the turning point, the environmental upheavals that would begin to dismantle one of the most powerful marine ecosystems in Earth's history. Asterisk